Hello, welcome everyone. Thank you for joining us today. My name is Simarpal. I'm a product manager at Intuit. I'm joined with my colleague Ian, who will introduce himself today. But today we are planning to share with you an overview of our machine learning platform and how it powers the real-time personalization of Intuit QuickBooks using Clickstream Data. Ian.
Hi, my name is Ian. I am excited to be here to share with you the Intuit ML platform and personalization. Thank you.
Okay. Thank you, Ian. So with that, as an agenda for today, I would briefly mention about Intuit and where machine learning is used in its product. Then at a high level, I will talk about the components of the platform. Uh, and after that, we'll go into details about the featureization and model inference pipeline. And we'll end up with a demo clip to show how the pipeline actually powers the in-product experience today. So at Intuit, we serve consumers through products such as TurboTax and Mint, and also small businesses and self-employed through our products such as QuickBooks. And in terms of where ML is used in product, a few examples mentioned are the search relevance for TurboTax, QuickBooks, and cash flow forecasting for QuickBooks, uh, and then providing proactive help within product and doing automatic transaction categorization, for example, in Mint. Now, if you read the mission statement of Intuit, then it says that the mission is to power prosperity around the world with AI-driven expert platform. Keeping that in mind, ML platform vision is to democratize AI ML development for anyone in Intuit by simplifying all the parts of the MDLC that you see over here through automation and self-serve user experience. Now, if we look at a high level, there are different types of technology used in each phase of model development within the platform today at Intuit. So on the feature engineering side, we provide Apache Beam, Spark, and Flink as a compute a framework running on Kubernetes infrastructure. And for feature storage, we use DynamoDB and S3. For model training and inference, we have AWS SageMaker. And for model monitoring and anomaly detection, we have in-house capabilities built. For the purpose of today's talk, we wanted to use case and walk you through the platform capabilities. At a high level, the user, whether they are using QuickBooks or a TurboTax, interacts with the product, and a series of events, which we call Clickstream, is sent to the Kafka-based event bus, now which are then persisted also into the S3 data lake. Then these events are used to do real-time personalization, real-time featureization. For prediction, features are fetched from the feature store and combined with the request payload to deliver the customer experience within the product. And we also have the, as I said, model monitoring and the feedback loop to further improve on the product experience and model performance over time. So now next I will gonna go deeper into how the featureization pipeline is built. So as a platform, so for the purpose of this talk, as we said, we will be focusing on the real-time personalization pipeline. So as a platform, we provide choice to the data scientist and machine learning engineers to use different combination of distributed processing frameworks like Spark, Flink, and programming languages such as Python, Java, and Scala. So in this case, the Clickstream pipeline to do featureization is built using PySpark framework running on Kubernetes-based infrastructure. The key components of the pipeline, starting from the left-hand side of what you see in the diagram over here. So we have a Kafka-based, real-time messaging system where all the Clickstream events, what the user is interacting with the product, they come into it. And there are several thousand TPS of Clickstream events that come in, and they are processed by highly scalable and distributed compute running on Kubernetes infrastructure. So in this case, the feature processor is written using PySpark. And for that, we also provide programming interface for developers to easily operate on data frame objects to apply their transformation and produce features. On the feature, once the features are produced, they are sent to another Kafka topic from where what we call as the ingestion topic, and this act as a shared message queue for both the stream writer that writes to what we call as the online store, and a batch writer that writes to the offline store. And the reason for this is to ensure there is consistency in feature values that are used at the time of inference and training, to avoid training serving skew. The data scientists use the feature values stored in the online store, which is backed by S3 and Hive table to do their model training. And at the time of inference, the feature values are fetched from the online store for real time in the real time fashion to provide low latency response to the application. The low latency store that is built using DynamoDB, where is built using that, and where we had taken several design consideration to support different types of feature values and associated queries. For example, few feature values could be like a profile information about a user, but then there are also features, which are tracked on certain dimensions, say time, for which some aggregations are applied, and then those values are actually fed into the model. Some of the other design consideration we have to do is around the compliance needs, such as GDPR and CCPA, where these feature values could be deleted if a specific user makes a request to be forgotten and removed from our databases. The last piece of the component that you see over here is the data serving layer. So this is a GraphQL based web service. Using this, the data scientists and engineers can fetch features as needed, and they can combine features across different feature set. In case of training, what this does is basically generate transpiled query that could be run on distributed compute to create training set that can then be fed into the model training process. And in case of real-time inference, it can directly return feature values from the store. In addition to what you see over here, we also provide users the backfill capability for in order to backfill historical value of the feature. Backfill is another key capability and not an easy one, as we have to do some orchestration between the backfill job and automatically transition to process stream events which are coming live. To make it easier for our data scientists and machine learning engineers, we have provided this capability as part of the platform, out of the box. And if you look at this whole pipeline, the end-to-end latency is actually in a very low single-digit seconds, and which worked for this specific use case around real-time personalization that we spoke about. So next, I wanted to talk to you about the development experience, what the development experience is like for our data scientists and engineer. Uh, to build like the feature engineering pieces, we provide self-serve experience on a developer portal where within few clicks the users are able to provision GitHub repository to write their processor code. Inside this repository, there are actually boilerplate code with simple examples for user to quickly get started and customize the code as per their needs. We also provide feature store SDK, which with using which the users can easily serialize the data and store those values in the feature store. In addition, we provide Jenkins build job to build the code and also a namespace on Kubernetes cluster where pipelines are run. Now, in order to make sure that the features, get properly stored with proper metadata, because this helps with the feature discovery, we have a feature set registration process also, where we actually capture the descriptive information about the feature and also other information such as compliance related to CCPA and GDPR. And as I showed in the previous diagram, there is an ingestion topic, that could be used in a self-serve manner to basically process the features into the online and offline store. And one last step is to create the schema for the GraphQL query for downstream consumption for model training and inference. And this is also provided as part of the onboarding process onto the feature management and the feature store. Another important aspect of these pipeline is to provide visibility into to our user into the operational metrics and cost considerations. So we provide these out of the box wavefront dashboard to track metrics around Kafka to see how many messages are getting processed and investigate if there are any consumer lags or not. So these things, all these abilities are provided in a much more seamless manner. As soon as they onboard their use cases, they are able to view through these wavefront dashboard. And the cost dashboard basically helps the users to look at the ROI of their investment as to how much are they spending in running these pipeline, to what value are these pipelines generating through customers in terms of providing benefit. And the last, importantly, like we provide the complete lineage tracking also for our users. Again, this happens through the metadata registry MDR component that I talked about earlier, to see how the pipelines are built, what are the components across the board, uh, connecting through different components as the pipeline goes from processing the data to storing the data and then making it available for downstream model consumption. Next, I would hand it over to Ian, who will walk you through the inference pipeline building experience and how does the model consume these features for inference.
All right, thank you for that, Simar. So today I'll talk about the inference pipeline that relies on the feature store in order to get the features and personalize the models. So what is model inference? As part of model inference, it covers deploying and hosting of the model, getting the features from the feature store, giving them to the model and getting a prediction. And last but not least, monitoring the model to make sure that it's producing the right results from my model efficacy, and also operational monitoring to make sure that the model is up, it's giving the response time in the expected SLAs. That way, the customer is getting really a personalized experience, and there is no lag between what the predictions are producing and what the customer is experiencing. So as part of the model deployment, uh, what happens is there's an interface. It's self-serve for the users, in this case, the data scientists and machine learning engineers. Everything is in a central dashboard that can be accessed through our developer portal. There is container orchestration, which the platform handles. Everything is running in containers. We make sure that it's meeting SLAs, it meets the security standards. And of course, you have the dashboards for monitoring, and you also have a status to know, is the model up or down? And I'll go into the dashboards at the end of this presentation when it comes to monitoring. So that is deploying and hosting. The next part is around feature fetching and orchestration. So for the feature fetching and orchestration, the way we've done this is that the data scientist is the author of a contract. We call this an escrow contract. The escrow contract specifies that these are the features I want to get. This is how I want to manipulate these features. And on top of that, it also specifies which model these features are supposed to go to. The contract is authored by the data scientist. It's abstracted away from where the data lives. So they just specify, this is the data I need. We on the ML platform side will go ahead and connect to the feature store, get the data they need, send it to the model, and then send the predictions back. So we've abstracted this so that there is a simple interface between the data scientists and the client teams, and that simple interface is just a REST endpoint that the client teams call. Next, I'll go a little bit into the details of the feature fetching because this has a lot of patterns. And given that we are talking about real-time personalization, I'll talk a bit about what are the different patterns. So first of all, this is for the real-time inference, even though we can handle offline, but because of this talk, we are talking about the real-time aspects of it. It's based on a DAG, and I'll show you how that is materialized via the different nodes. And I'll go into details of the different feature fetching mechanisms and orchestration. We have model/data dependencies, parallel execution, data transformation, or what we call last mile transformation, and also asynchronous execution. All these are the different ways we can get features from the feature store and feed them to the model. So for the feature orchestration, I'll start with the model and data dependency. The way you read this is you read it from the bottom going up. The one at the top, model 2, that is what will finally be executed. So for the data, assume that all this data is coming from the feature store. So you can see that you can have the data come from the feature store, and then the different nodes can manipulate the data in order to get it into a certain format and then move this data to the upper nodes. In this case, you can see that model 1 gets the data from the feature store, which is data 4. It gets the output of that, and then that will feed into another model. So you can see model 2 depends on model 1. At the same time, it also gets the data from the feature store via feature 4, and all of these will feed into model 2. That is for model and data dependencies. The second one is parallel execution. And what this means is that if you see features 1 and features 4, these will be retrieved from the feature store at the same time, and then they'll feed back into the different aspects. In this case, feature 1 will be used by another processor to generate feature 2 and feature 3, whereas feature 4 will be used by model 1, and then model 2 will also use the same feature. But when we get the features from the feature store, we'll get features 1 and 4 at the same time. And we can get up to n features from the feature store at the same time. We have some models that actually rely on 300 features. And then the other part that I want to talk about is you can also get features after you've done the parallel fetch. You can also do some light aggregation, as Sima talked about, and then the aggregation of that data will be sent to the other upper nodes, in this case, model 2. Now, how does this affect the personalization? For example, if we take features 1, 2, and 3, it could be that the features that go into model 2, it's an average or a summation of these, and depending on the average, the experience will be different for the user. So the red arrow indicates a point within the node that is doing some feature processing. Now, all of this that I'm talking about happens on the model serving layer, and we on the ML platform, we handle that. Last but not least, I want to talk about the asynchronous nature. What this means is that you can have two models, even though there's an intermodal dependency, they can send their own predictions independently of another. What this means is that model 1, after it has done its processing, it can send its output to the calling service. At the same time, model 2, even though it's depending on model 1, it will independently send the output of the predictions to the upstream services. They do not have to wait for each other in order to materialize the final predictions to the upper layer. So all of these different patterns are handled by the ML platform, with the user just specifying that I want these features to be gotten from the feature store. Now, last but not least, I'll talk about the monitoring. In this case, you have the monitoring of the model predictions on the operational side. What this means is that, one, you the user can specify, I need to get these requests per second, and I need to monitor them on a percentile basis, on a mean basis, so that if there's anything that goes wrong, they can take some action. And this is provided by the platform right out of the box. The user does not need to do anything. And one of the things that also we take care of is to make sure that we are monitoring the feature orchestration processing time, because of the online nature of these models, we need to make sure that the predictions or the feature fetch are produced in a timely manner. So we always monitor that. And if the orchestration is taking long, we can have an alerting and have users take a look. The other part when it comes to the model monitoring is monitoring the predictions themselves. This is the actual predictions that are coming out of the model. In this case, you're monitoring them on a statistical basis. The table on the left shows you some of the statistical metrics that we are looking at: mean, max. You can look at the number of null values. Anything that is anomalous is monitored, and the user can set the threshold of alerting so that downstream systems can do the featureization, to do retraining, or the users can take some other kind of action. The other part is we also have the ability for users to specify different kinds of monitoring depending on the model itself. For example, for binary classification, you can have confusion metrics, accuracy, precision, recall, all sorts of things. So this is also provided by the platform out of the box with the user specifying the alert levels and the thresholds and also which teams to contact. So what does this all mean? For the real-time personalization pipeline, we talked about the featureization whereby you have your clickstream events, you're doing the online featureization on the streaming data, you're storing the features in an online store. On the inference side, the model is deployed, it's up and running. The ML platform is getting the features from the feature store. It's handling the orchestration of various features, combining them and doing monitoring. All this ends up providing a personalized experience for our users based on the data that is unique to them, while ensuring that we are powering prosperity for our customers. And now I'll go ahead and show you how this looks like from a user perspective, and you'll see how this is actually realized for our users. So as this is loading up, I'll show you what this looks like. So in this case, give me a second. So what you're going to see here is a self-help customer. They are going to be within QuickBooks product. They want to log transactions because they want to keep track of the miles they've driven so that they can get reimbursed when it comes to tax time. So the user is going to go to the transaction tab and they are going to choose to enter their transactions manually. And part of that entering the transactions, they're going to log their miles. So you'll see them going to the miles tab on the left-hand side here. They'll log in, they'll put in the address of the starting point, and you'll see that it's not clear what exactly they need to do. And finally, they'll go to the tab here for an assistant, and you see that the data that is presented to them will be dependent on the data or on the previous actions that they have taken. So now you see the user, they are logging a transaction. They're adding the transaction within QuickBooks. They try to connect to their bank, but then they decide not to. They go to the Mile tab, and they're going to record a trip. So as they're recording, they're putting in the starting address. And now they don't know why they can't save, and they realize they have to put in the trip purpose. So now they want to add another transaction. And they're selecting what kind of category this transaction falls into, but they are not really sure. Is it insurance? Is it vehicle? They save that. Now you'll notice that here, once they've clicked the help tab, I'll take a pause here and I'll show you. You'll see that based on the transactions that they have, the help tab here, it's going to show them information based on the previous screens that they have seen. So in this case, there's a help tab for transactions. There's a help tab for trip. There's also another one for the categories that, because they're trying to categorize some transactions, and also they're showing for the business miles. Now I've gone to some websites and they have a self-help bot, and what it will do sometimes it will just show you need help. But in this case, as you can see, that this help is really personalized for them in order to show them the relevant help topics. And of course, when the user takes action here, the information that is provided is really relevant to the transaction. And of course, you can see that these other subsequent help tabs, they're also dependent on the previous clickstream data or actions that the user has taken. And that marks the end of the presentation. Thank you very much. Sima and I will be available via Slack to answer any questions that you might have, and we look forward to the discussion that this is going to elicit.
Yes, thank you very much, guys. It was great sharing our platform and information regarding our personalization pipeline. Feel free to reach out, as Ian said, on Slack.